Do it. Okay. Today's topic is spatial model of segregation. In fact, lecture will be, well, quite short compared to our previous lectures. We'll just talk about this model. So the name and the idea comes from a very famous paper by Thomas Schelling from 1971 that's called Dynamic Models of Segregation. He actually pretty much started this entire domain of modeling, and today, it would be called agent-based modeling. And so the main idea is that you do have certain agents, and those agents can do certain actions, but the point is their actions and what they can do is local. So they are sort of micro actions, and those micro actions can lead to macroscopic changes in the entire system. And so the entire story about this sort of how micromotives create macro behavior of the system. Or in other ways to put it, how like personal preferences lead to collective actions. It's somewhat, should remind you a little bit about the model we talked several lectures ago about Granovetter model, collective actions. So, but Thomas Schelling was interested in a very, very particular problem. And this problem, it exists up to date, and it's right into your face, the problem of racial segregation in the cities. So the segregation means that people of the same color tend to live next to each other, and cities are very, very segregated. There are enclaves of say, African Americans enclave, of white people enclave, of Asian Americans enclave, of Spanish, Mexican people, etc. So, but when you interview those people, they typically quite tolerant to having people of other race living next to them. In spite of that fact, you get segregation. People still, in spite of the fact that they're tolerant to having even like half of their neighbors to be of a different race, people still eventually move and settle such a way that they live mostly with the people of the same race. And that's true not only with respect to the race. Race is just sort of the most obvious factor. But the same thing happens with, like, say, native language. And again, in US, there are a lot of examples. There was, like, say, in San Francisco, there was Little Italy, there was Little Tokyo, there is Chinatown, which is completely populated with people speaking, say, Chinese, right? So that's the question Thomas Schelling was asking. Pretty much the question was, okay, so how come that's happening, right? Though each and every person by itself doesn't mind having people of other nationality, language, or income, ethnicity around them, on the macroscopic level, we get very, very strong segregation. And to answer that question, he actually proposed a model, and we'll talk today about this model. And it's agent-based model where there are certain rules are given to agents, and then there is a simulation dynamics, and we'll see what happens after that. It is very similar, somewhat similar to the simulation we did for when we talked about infection and disease spreading. So first of all, the notion. Imagine that we have agents of two different types, say A and B, or here is green and blue. This problem does have a geometry embedded in it, which means we're looking at the geographical location. And the terminology is the following: two types of agents, green and blue here, and on the left picture here, it's integrated pattern where it's totally randomly assigned sites, and you see that it's a mixed, very, very mixed population. On the right, it's clear segregation, right? So people green live on the left, people blue live on the right. And so you should think about this as, okay, here's a coordinate system, X, Y. Of course, you can think about this in a high-dimensional space, but it sort of doesn't make too much sense because we're talking about segregation in this real world. Though one-dimensional problems are still, of course, of interest. So you might want to consider sort of one-dimensional line, and then it's also very clear what segregation will be in a one-dimensional case, right? So somebody on this side versus someone on that side. Here's an example. This is a data from US Census and a bunch of American cities that are very clearly segregated. So you can see Manhattan, a bunch of white people, black people. Here is Seattle. This is Asian population. Take Los Angeles. This is a white population. Here's black population. Here's Mexican. Chicago, the same story. So we have enclaves of Spanish-speaking, Mexican population. We have a bunch of white people, black people. So there is a very strong segregation in all those cities. Though, if you know, like America is very, very much diversified, and there is a lot of attention being paid to equality of different races. So the question is, how does this happen in spite of that fact? Here's another example. This is graduation rate. It's actually it's high school graduates. It's people who actually graduated from high school. This is a Bay Area. If you already watched San Andreas Fault movie, you might have seen this type of picture from the top. So this is the Bay Area, San Francisco. Again, the red is 100% high school graduates. Yellow colors are less, and you also realize that people who did not graduate high school, there is enclaves where they live, and again, they tend to live together. And here's another example, which is actually had nothing to do with race. It's presidential elections. So that's people's preferences, right? Democrats versus Republicans. And you'll see instantaneously that, yes, California is Democratic, Seattle is Democratic, New York, Boston is Democratic. And then there was like sort of Democratic pieces all over the country. But if you notice here, there are big chunks of red land. So again, people tend to either live based on their preferences, or maybe if they move in and then they change their preferences eventually. But it's quite consistent across all those different examples. So here is a model, Schelling's model of segregation. Let's assume that population consists of two types of agents, okay, two types of people. And you can think about sort of these types as being based on race, being based on income, being based on whatever you want. Sort of the binary decision, binary two options. And the idea is original idea, and we'll sort of look at first at the original model, and then we'll see what's new has been added recently. But the original Schelling's model was agents reside in a cell of the grid. So we have a grid. Just put a grid on a surface, and agents reside in the grid. Okay, and say there's an agent A living here, and there are neighbors of this agent. And say A, B, B, A, B, A, B, right? So it's a sort of neighborhood, and the agents of two types that can live in that neighborhood. And for every agent, you can look at nearby cells. Or in fact, for model to work, you need to leave some empty spaces. So I'll keep here. I'll leave this thing vacant. I'll leave one cell vacant. Okay. So the point of the model, the core of the model is the following. Every agent, every person wants to have at least some fraction of agents in the neighborhood of the same type as he is. So if this is an agent A, and again, we're like doing right now exactly Schelling's model, he has in his neighborhood agent 1, 2, 3, 4. So 4 agents of his type. And actually, sorry, 5 according to this picture, right? So 5 agents of his type and 2 of the opposite type, right? And overall, we can have 7, there are 7 spots. And what we have is at this moment, there are 5 out of 7 is of his own type, right? And 2, 7 of the opposite type. And so, you know, if agent A, the person has a threshold that is, let's say, you know, he's happy if, say, I don't know, at least 1/2 of the people that surrounding him is of his type, then, you know, he's happy in this picture and just gonna stay. The interesting thing happens is when we add dynamics, and dynamics even the following. If by whatever reason this agent becomes unhappy, well, I mean, and the reason would be the population, say, by whatever reason there is a change in population and we got more B people moving in, then the person of type A will feel uncomfortable and move out to some available location on the grid. Okay? And that's the process that will be happening for every agent. And eventually, the question would be, all right, you know, if we let the simulation run for a long time, if the thing is going to stabilize, and when they stabilize, you know, what's going to look like? So that's pretty much this Schelling's model of segregation. Oh, and here's an example, another example. We're looking right now at the central agent here, X, and there is a neighborhood, and 7 is an empty spot. And let's say if the threshold is you know, 3/7, and that means agent A is happy when there is at least 3 out of 7, because there are 7 neighbors around him right now, right? 3 out of 7 of his color, he is satisfied. And say in this case, on this picture, there are only 2 agents of his color. So based on this model, this agent will try to move out from this location. Okay, so that's sort of the whole thing. Now, in order to move somewhere, he needs to make sure that the place he's going to move to, you know, also will be good enough for him to live. So in that new location, the conditions on the neighborhood will satisfy him. And that's true for every node. So pretty much in the model, every node or every agent takes a turn to consider the neighbors and either stay or move. So this is a picture, this is a figure from original paper by Thomas Schelling, 1971, of his simulations. And there are 2 types of agents here, right? There's this agent and that agent, and there are empty spaces. And here's the simulation he has done. And in fact, most of the simulations they did were done by hand. And you can see that after a while, he got, you know, very clear segregation patterns, which means bunch of this zeros or odd type of nodes got together. Now, of course, today you can do much better with simulations and get much cleaner pictures. Again, here we have two agents, red and blue. There is a 5% vacancy rate, so there is 5% of empty spots where agents can move. And tolerance here is 1/2 in this experiment. So which means agent doesn't move unless unless more than half of his neighbors are of different colors. That's how you start. You start with a random distribution. And that as time proceeds, you start seeing these big islands, then they merge together, and then we get like complete segregation. So the simple, very, very simple dynamical rules actually lead to pretty much complete segregation in this society. And what I want to emphasize is that the tolerance level is is pretty, I don't know, high or low, but it's 1/2, which means that the person is quite tolerant. He doesn't require that 90% of the people be of his type or his color. It says, okay, I'm cool with half of the people of being like me, living next to me. But even that leads to a very strong segregation.
Sorry, a question.
Yeah.
First of all, the spot that the one unsatisfied moves to is chosen at random, yes?
There are different flavors of this, but it's some flavor of random, yes.
Okay. Another thing is, if the tolerance is half, then the shapes that should be achieved in final picture can have small angles, because the person on the angle will be unsatisfied.
Right. So what you're saying is, let's say, if you're on the boundary, right, yes, and you want, let's say, half of the people, right? So you get to have, this is your like little flat structure. That's what I mean, right? But remember that if we're speaking here about the grid itself is sort of very, very fine, right? So they're like, what happens, you're right, the boundaries should be smooth, but they don't necessarily have to go absolutely straight through the whole thing. So I totally agree with you that in this case you cannot, say the situation, say like this. It doesn't draw it. Situation like this, with a sort of little sharp enclaves, is not going to happen. But so there are 2 points here. First, you're going to see that in spite of, it's not only 0.5. I can take threshold of like 1/3 and still get the segregation. Now there are different stories happens here. There are this model. Say it again.
May I ask a question too?
Sure.
You talk about static equilibrium, but is there, for example, a dynamic equilibrium? For example, if in your picture there is a half red circle in the right, and if we take tolerance less than 1/2, I think it will be constantly moving, because people on the edge won't be satisfied with their position and try to move. But you draw this picture like the static equilibrium is no, it's no.
Yeah, understood. It will be so the answer is yes, it's going to be static. You will see in a few examples on the next slides.
Okay.
So it's gonna okay. So what's going to happen is the following: this model possesses phase transition, and that means there will be a range of parameters where you can actually get the sort of segregation, and the range of parameters where things will stay mixed up. So we'll see it in a second. Now back to the point you were asking also about the separation lines. It's actually interesting that the model has been proposed by, well, Thomas Schelling. He's an economist, right? And the model has been out there for like 40 years, and only like within let's say last 10 years or so, physicists started looking at this model, and well, there are several interpretations. One of them is actually try to make a parallel between this model and mixing of liquids. And when you're talking about mixing of liquids, that's when you have surface tension in liquids, and then when you try to model, how the boundary can actually go because of this sort of half of the voxel field. So, again, the model comes from economics. There are some projections onto like physical properties and this sort of things with continuity. Here is an example. Again, so what we see here is the following on this matrix. And this is from the paper by Govin as a previous slide. So what we see here, these are different densities of vacant spots. So, number of 2% of the points are vacant, 6%, 12%, 18%. Now, why these vacant spots are important? Well, because if you don't have vacancy, then, there is no way to move in this model. So in this model, you cannot just, two nodes do not just simply interchange their sites. They have to, the one node has to move, one agent has to move to available location. And these T's are, well, what I called on the previous slide lambda. These are thresholds. And, if you check this out, you realize that there are a lot of, there is a sort of space here, right, where you get segregation. And on the left and on the right, you do not. And by the way, they also show here slightly different values of lambda, like 3/7 or 1/3 in this case. So there is entire phase space of lambdas and draws where the phase transition is happening. So just if you think about this, the point is the following. Here, and we'll talk more about it, but here, for example, the threshold, the tolerance threshold is very, very high. And that means people are generally, happy where they are. So if my threshold is say 90%, and I'm happy with 9, or my threshold is 100%, right? And I'm happy with whoever lives around me. There is no reason for me to move. Okay, and that's what sort of happens on this side. On this side, threshold is low, which means I always want to move. And with this level of fill up, there's really just no place for me to move. So it doesn't matter where I move, my threshold still will not be satisfied. And so, I cannot move. And so that means, on the left, there is a mix. There is a mixture because people just simply cannot move physically. Here, they're just happy where they are. And so it's also clear that if you increase, for example, the vacancy, if you sort of go that way and increase the vacancy, this area will be shrinking simply because people will be able to move more. And that's, some of the practical sort of conclusions from this model is about population mobility, right? So you want to have happier population. Well, make the population mobile. So, okay, that just was sort of the pictures. Now let's take a look at the model itself, so you can actually model it. Here are the few parameters. So we have, let's say we have n nodes. Oh, and by the way, what we're going to do is we start with the original model, and then we of course think not about the grid but network, right? So we can actually do this on the network. So we have n nodes, and here it's called theta, the fraction of occupied nodes by A and B. So compared to the previous slide, the raw was 1 minus theta. And so total number of agents of type A plus agents of type B will be theta times n. We can calculate proportion of unlike nearest neighbors. So the point is, for every node, and I will start already drawing networks, for every node and every nearest neighbor, calculate how many of neighbors are of opposite type, right? And let's say here we have, for node A, we have 3 nodes of type A, but what we're interested in for node A, we're interested of number of node of type B surrounding it, okay? And since these are economists and this is economic model, we're going to introduce utility function. And utility function just is very, very simple utility function, which says, okay, if the number of foreign or unlike neighbors is less than threshold, the agent is happy, utility function is 1. And if the proportion of unlike nearest neighbors exceeds the threshold, utility function is 0. And what happens is really every node moves to maximize its utility, right? So every node goes around the network to maximize its own utility. And this is, for example, very, very simple correspondence in between original Schelling model, where you have a grid and cells and the nodes in the cells. We can represent it as a network. Now, in the original Schelling's model, for every agent, there are 8 nearest neighbors, right? So you consider 8 nearest neighbors. And, well, that's how we represent it here. For me, it actually reminds more, speaking of Russia, it reminds me like, I don't know, country houses, where you get neighbors all over the place, right? And it's all on the grid. So, but of course, the model is going to work even if you, say, consider as the nearest neighbors only these guys and do not talk about diagonal. Or you can put any substrate, any network, and look at on any possible network. It doesn't really matter. And that's what we're going to do in a few next slides. Okay, so the algorithm itself. We start running time. And on every time step, we randomly select an agent and compute the utility function. And if utility for that particular agent is 0, we move him to a new location. And here are the few tricks. First of all, movements can go either just to completely random location, or there are sort of flavors, of course, of this model where, for example, the person will be moved to a nearest available location. So, it makes model a little bit more complicated, maybe a little bit more realistic. So you don't move anywhere in the world, right? You move still to the location, to the preferred location, right? But the important thing is the new location the agent has to move should have, for that particular agent, utility equal to 1. So it should maximize its utility. Now, if there is no available location, then the system eventually reaches a frozen state where no one can move at all. So the outcome of this whole process, there could be two outcomes. One outcome is when everybody moves this to a preferred location and the utility is maximized. So since utility that every node has when he is happy is 1, then total sum of utilities will be just equal to the total number of agents. And the total number of agents is the theta times n, or NA plus NB. And that really means that everybody's satisfied, everybody's happy. But if there is not enough free space, or agents are very picky and have very small threshold, then their utilities will not be maximized. And there will be some agents with utility equal to 0, so the sum of the whole utilities will be less than the whole thing. And by the way, like any times in economics, you can also calculate total utility for the society, right? If the society in general happy or not, and you can think about this Pareto and all those kind of things. Okay, so that's really the algorithm. Now, last point to the algorithm is actually how do we measure segregation, right? Because we need to somehow distinguish situation where you have bunch of nodes and that either of the same type, right, and they connected to each other, and whether the situation where we have sort of this type of situation or okay, let me draw this. We have something where the population is entirely mixed up. Okay, something like that. So the question is how to distinguish those two cases. And I mean, of course, we do it visually, but it's good to have some index, some measurement. And Schelling proposed for his model mixing index that really just says, okay, let's calculate the sum of the of this PIs and PI are the fraction of the foreign nodes in your neighborhood, and just normalized by the total number of agents. And if you completely segregated, right, if the connections is only with neighbors you like, then the segregation index will be small, and otherwise will be large. Freeman proposed his own segregation index that also based on the ties between groups. And looking at the picture here, I also want to remind you this assortative mixing. Remember, we talked about it before. That Marx-Newman metric that tells you that okay, well, it increases if there is a connection within the class, right? And so in this sense, it also will be sensitive to edges within class, right? And will not give you anything if there are edges between different classes. And so you can also use this assortative mixing measure. But classic here is typically people, when they look at Schelling's model, they look at his mixing index. All right. So again, when people are connected only to their peers or to the people that are alike, the Schelling's mixing index is small. It's small because this number, which is a proportion of the sort of opposite type of neighbors in your neighborhood, is small, right? Or sort of 0. Then we have, if this metric is 0, we have a completely segregated society. All right, make sense? Okay. So I'm going to show for the next few slides. I'm going to show the results of the work by Arnold Manas, very good paper where he tried to model things on a different graph types. And here's a few lattices. So there is a regular graph, there is a random graph, geometric random graph, then there is a scale-free graph, and then there is a sort of fractal type of a graph. Now, he didn't want, if you remember, of course, on all those graphs, there are very different degree distributions they have. And for this type of model, what's important is a local neighborhood. And so what he did is he augmented those graphs, creating neighborhoods where he connected nearest neighbors and make sure that every node has a degree 10 by connecting the node to all the 10 nearest neighbors based on the graph structure. So, if you have a graph and there is a graph structure, what he would do, and let's say he says, okay, I want the node degree to be equal to 10. So right now node degree is 1, 2, 3, 4, 5. So I'll directly connect to other nearest neighbors. To other neighbors that are, say, 2 steps away, and make them direct connections until I reach degree 10. So he has done it so he'll have equally dense graphs for all of those. Now, again, this is a research paper, so I would say you could probably run experiments directly on those graphs, but he believed that this is a better way to do it. So anyway, so the results will be given for these graphs. Here is an example. Here is an example of spatial segregation. Again, at lambda 0.5, now it's 0.8 or theta, which is 20% vacancy rate. And here is the results, right? As you notice, whether you look at the regular grid or you look at the random or you look here, you have segregation everywhere. So here this boundaries and boundaries, more boundaries. Well, you can see it. So what this shows is that Schelling model is quite stable with respect to different structures. So it's not only regular grid that creates segregation, but also all kind of structures that we see here. You'll also have a segregation pattern. Well, in fact, and I think this is sort of the critical graph is here. So what we have on the y-axis is this mixing parameter. So the level of mixing. And on the horizontal axis, there's this tolerance. Well, it's just given in a percentile. So this is 0.5. This is 1. And we have different graphs. We have a grid, which corresponds to our regional model by Schelling. And here's a random network. Here's some example of scale-free and fractal. And you can clearly see different phases here. So when your parameter space, where the tolerance is somewhere here from like 30 to, 0.3 to 0.6, 0.7, here the mixing coefficient is very small, which means we have a segregation. We have sort of unstable situation here, but then we have a complete mixing. And there is a very strong mixing here. And the explanation is, pretty much as we discussed, over here, the tolerance threshold is very high. And if it's 100, then person will never move at all because he is always happy, doesn't matter who lives around him. But even in this case, you can have 1 or 2 people of different race or whatever next to you and people still happy. It's a different story on this side of the scale. Here, people just unhappy, but they cannot move. Okay. What's another important point, very, very critical point, again, I want to emphasize that, this really means whether it is, let's say lambda is 1/3, it really means that, the tolerance rate is pretty high, right? Or lambda 1/5, lambda 1/2, 50% really means that you can have, half of the people of a different type, and you'll be happy. Here is 1/3. Here is actually 2/3. But though there is a mild preference to people of your type, which means you still prefer them, you get a segregation on the big picture. And so that's probably the biggest finding of the model, right? That the local preferences, people are not so people kind of, though people tend to be quite tolerant, right? People sort of on a personal basis, they're not racist. As a system, it becomes very, very racially segregated. It's kind of also in the direction of those sort of crowd effects, where you have, again, as we talked previously, the effect where there is a sort of micromotive creates very different microscopic behavior of the entire system. So getting back to this picture, as we discussed, this part corresponds to people who would like to move but who cannot move. And the way to prove this is by monitoring the sort of the happiness level or the satisfaction level or the values of U's, right? And so on this side, the sum of UIs, and on this side, the sum of UIs will be much smaller than here, right? Well, the great thing about models is that, within the model, you can actually change sort of parameters or change the model and see what happens. And one of the ways here would be to, well, let's just let these people move. If they're in the frozen state because there is no space, there is no place to move, what we can try to do is we can try to let them actually change the location in spite of the fact that, say, in the new place, there is still, that their utility is not 1, but still 0, but we still let them change the place, okay? In the hope that, some other things around might change, and they'll be happier in the new place, right? Because again, this is an aggregate behavior, and so their happiness is determined by their neighbors, and neighbors might also move. So in some sense, if you're familiar with, say, simulated annealing, the optimization technique? Simulated annealing. Имитация отжига. All right, so in the optimization scheme, what you do when you try to optimize something, I mean, typically you do, say, gradient descents or any type of descents where you have optimization function and you want to find a minima, right? You're just trying to find the path that always goes down until you reach the minima. That's sort of traditional thing. The problem with those optimization methods is that if you have this kind of situation, the algorithm will reach this minima, local minima, and get stuck in it. It will never go out of the local minima because it always tends to go to a location with a smaller energy. And so simulated annealing method says, okay, always go downhill, but sometimes go uphill. And that process, that sort of change allows you to get out of the local minima. So the same here, the same idea is here. Agents always move when there is a empty spot that will be good for them, but sometimes they can move even if the new spot is not that good, but just let's move and see what happens. And that's what happens. It's kind of interesting. that even if you add this sort of random noise, what they call random noise, but that means you're allowed to move even if that move does not increase your your utility function. What happens is, say for scale 3 and for fractal network, you actually resolve this issue. So which means people can now move from there, right? For grid and random, that still doesn't help. You still have this pretty mixed up phase. So again, what happens here, if you notice, when people have very, very low tolerance threshold, right, the mixity becomes also very small for those two things, which really means that we get segregation. So now, we have segregation pretty much all over the place here, but for these two models, it's not happening. I should point out that these are results of this paper, and it's pretty much, I would say, active area of research. And myself, I haven't tried this type of models, but probably makes sense to see how they actually work on those networks and see if this type of changes, if we can sort of reproduce his results, because results are quite interesting. So it says that this random noise, so which means sort of the opportunity to randomly move from one side to another in spite of in the not changing utility, it actually affects this type of networks, but does not affect grid or random. But so that's sort of what's in the paper. It's really sort of, I think, it deserves further investigation. And here's an example. Couple more things that you can think about, you can say about the segregation. Notice that, of course, depending on initial conditions, so depending on sort of how things initialized, you might end up, with a different segregation patterns, and that sort of makes sense. You'll still have segregation, but it'll be different segregation. Another point from this paper is also very interesting, that these are different runs of segregation process that happens with different values of parameter lambda, where lambda is tolerance, right? And there are a couple of things that you can notice. You notice that here there are degrees with very high centrality. In a fractal world, they're sort of central, and they remain vacant. So that's another interesting observation. So I would say an interesting research problem would be to actually look at look at the networks and compare vacancy rate and versus correlation of the vacancy rate versus, say, centrality of the nodes, or between the centrality. Remember that all those centrality metrics, they're tied up to the topology of the network, and so it is very possible that eventually some nodes, for the system, it will be optimal to have certain nodes vacant. That also, of course, will have implications. Let's say if you want to design cities in a certain way, you probably certain location in the city you might want not to, say, build in housing for that. So there are a lot of interesting things you can still do with this model. The final thought here is that, in fact, there is a very clean and nice description of this model that comes from physics. This type of models has been has been studied at the beginning of the 20th century. One of the models called Ising model or spin model. The point, but in short, the way to sort of put this in a nice framework is the following. Imagine that we have this two type of agents like we do have, and now let's use the state variable or sort of signal variable that really can take three values: +1, 0, and -1. And it is +1 if we have agent type A. It is -1 if we have agent type B. It is 0 if there is no agent. And so we can describe the state of the system just by writing this state vector, where sigmas are those +1, -1, or zeros, depending on the state of the system at the moment. We have an adjacency matrix. Then, using these sigmas, we can calculate the fraction, for example, of vacant sites easily, because, again, sigmas, if they're occupied, it's either +1 or -1, and so, this sum will just tell us how many occupied sites are. And we can also easily calculate proportion of unlike neighbors, that parameter pi that we use, the following way. Now, again, think about it this way. If sigmas taking values +1 or -1, and we're calculating the proportion of sort of foreign type of agents in the neighborhood, what this does is the following. If the neighbors are of the same sign, 1, 1, or -1, -1, this is equal to 1. Now, this is equal to 1 always when their things are occupied. And so if these are of the same type, this becomes 0. If they are of the opposite type, this guy is -1, this 1. So this contributes to the sum, and that actually means my formula has a mistake. It should be divided by 2 here. And if one of the sites is not occupied, sigmas are 0, so there is no contribution to the sum. Anyway, you look at this formula, you realize that it computes the same thing as we did before. And so you have a state space, and you have the proportion of neighbors, and you can do this, compare it to lambda, and based on that, you can go and change the state space. Okay, and that's how you can sort of model this easily, model this dynamic easily using this description. So bottom line, again, the critical findings on this model is that spatial segregation is taking place even though every individual agent is not necessarily or actively looking at, which means it might have minor preferences. That is, that say 1/3 of neighbors he wants to be of the same type. So the tolerance is high. But even this sort of 1/3, which seems to be a threshold for a lot of models, from where you start getting segregation. Network structures does affect segregation, and as a result, there is this sort of particular characteristics, like fixed characteristics, like for example race, can become correlated with, say, location in the graph. The interesting thing about this model is also, well, first of all, it's really applicable to what's happening in our lives. And the second thing is, it seems like there are still quite a few things in the model that hasn't been explored. And so that can be a good opportunity to look at how this model behaves on the different networks, with different set of parameters. That's kind of a topic for research if somebody's interested. References, the original paper by Schelling, then there is Linton Freeman, who talked about segregation, and a couple of papers, more recent papers on the subject. And I used slides, I used pictures from his paper. So that's pretty much it for today.
I have a question about the structures of network. When we allow the unsatisfied to move to surpass local minima, I think that if there are enough vacant spaces, the equilibrium with total segregation is achievable even if the tolerance is 0, if we can segregate them in a way that there is a layer of vacant places between two areas, and it's achievable even in regular network.
Totally agree with you, and that's why this fill up parameter is also parameter in this phase diagram. You're absolutely correct. If you can have a layers of sort of empty spaces, yeah, you can definitely achieve that. I mean, and that's, if you think about real life, that's how Geta organized. Or let's say we don't see it. Well, we already see it in Moscow too, but in US you see it very clearly. It's a freeways that splits the cities. That creates this sort of 100 meter of no one land, where freeway stands, and it's entirely different communities on one side of the freeway versus another side of the freeway. And we start seeing this in Moscow too, with with both third ring, second ring, and all those things where you cannot actually cross them anymore easily. Totally agree. The other thing is also interesting, that when you have networks, remember we also talked about it for a long time, lots of these networks do have this clustering properties. There are clusters, there are bunch of nodes that are tightly connected to each other. So it's very clear that if you try to run segregation model, most likely within the cluster, in order to have the high utility, everybody has to be of the same type, right? Because there's a lot of connectivity in there. And so you might think of that, if you have sort of a network with a bunch of clusters, and we did a clusterization, one of the interesting experiments would be to actually see if this is true or not, but that sort of the segregation will happen by cluster boundaries. Right, so different clusters will get sort of different type of communities. Most likely, that's what's going to happen. But again, I haven't done experiments, so that's something for investigation.
Thank you.
Okay, so that's it for today. Let me do a couple more things. Just give me one sec.